Okay. Just. Oh man, my brain is melting. I can't remember anything. Okay, so I'm going to do a little recap. I really do, but we don't have time for that.
The sun's out.
Sun's out, sun's out.
Maybe. I'm smelling too many fumes over here.
Your brain is just melted.
I'll tell you in a second. Okay, give me your focus here, everybody. Let's end all side conversations. Okay? Let's, I was telling B6, if this isn't something you do in your life, I highly encourage you, and it's something you have to like train, right? Like, especially if it's not your habit. But something that I feel helped me be successful is, because I feel like I was a pretty successful student, and I was pretty successful in things outside of being a student, like an athlete and other things. And one of the things I feel like that helped me is that I always gave 100% in the moment I was in. And so like when I was in class, I didn't let anything else in my brain. And I was just focused in class, like on that topic. You know, and when I went to running practice, I was just focused on running. And that's all. I wasn't thinking about anything else except for the moment I'm in. Some of the people who consistently have performed with the highest scores, now I can't say what they do outside of class, but one of the things I can say they do in class is they're attentive during the lesson. That they are very attentive to what we are learning in the moment, especially if you're a busy person and you don't have time for that much outside, right? Use the moment you have to get as much as you have it. So I'm going to recap last time's lesson a little bit to kind of lead into today. Oh, if you go to the what did I miss, is that what you're asking? You can find the papers from last time. Yeah. Okay, so last time we talked about pretty much an intro to acids and bases, what they are in terms of a formula. Identifying conjugate acid-base pairs was kind of a big part of the homework. And then we led into the conversation of pH. The equation for pH is, remember? Log. Okay, so the negative log of, good. And you don't actually have to have that memorized, it's on your formula sheet, but you probably will by default. So anyways, this is pH. pH is a measurement of the amount of H plus floating around in a solution. It's just a scale set up to separate these classifications of acids and bases. If something has a very low pH, meaning less than 7, so 7 is the middle of the pH scale. Remember, that's pure water.
Oh, I remember pH.
Is it coming back now?
It's coming back to me.
So anything less than 7 is classified as an acid. Now, what does that mean about the H plus concentration?
There's a lot.
Good, there's a lot of it. So acids have a lot of H plus, but because of how log functions work, the bigger the number here, the smaller the number on the scale. So you gotta kind of be careful with that flip. And then vice versa, anything bigger than 7 is classified as a base, and bases have very little H plus floating around, but they still have H plus. What do bases have a lot of floating around? Good, so bases have high amounts of hydroxide floating around, and acids have a very low amount. And then neutral is because these two things are equal. Yeah, Allison.
So how would you relate like OH minus to pH? That's not.
Ooh, like the amount of OH.
Yeah. So like if like the pH was like 6, how would you find the amount of OH?
So if the so I would go typically, so remember we have a pOH scale, and they're related through 14. So mathematically speaking, if you do 14 minus pH, that takes it into the pOH side of things. And then if you know the pOH, you can do the inverse log, so 10 to the negative. So if you did 10 to the negative pOH, that would tell you how much OH you have.
Unless it's water.
But it should still tell you the amount, but it would be equal still. Yeah, does that kind of make sense? You have a question back there?
Oh, was I saying, if you have like the pOH, it's like the pH plus the pOH equals 14.
Yeah.
But if you just like get the OH, could you just subtract that from 14 and get the pH?
Yep, and that's normally my preferred route. You'll see today as we work with our equations, like there's sometimes different routes you can take and still get the same answer. That is my preferred one because it feels the easiest. But yeah. Okay, so with this idea of acids and bases, oh yes.
It's not in there.
You want to bet?
No.
What? I thought it was supposed to be in the very bag.
No.
It's the power of a mother.
Oh, I thought we were like unit 10.
I know, it feels like we should be right now. That's okay. I'll forgive you. Okay, so today we're getting into expanding, really like, this is still the goal today, is focusing on this concept of pH. We're going to extend now our understanding of acids. So last time we learned acids, bases. Now we're going to learn within the acid family, within the base family, those can be separated into what are called strong versus weak. Where you have strong acids and you have weak acids, and you have strong bases and you have weak bases.
Like for instance, citric acid would be a really weak acid.
Yes, citric acid is one of the weak acids. Yep. Which is why it's not as bad for us to eat.
I mean, not a
Not
lot.
as bad.
I mean, you probably don't want to just suck on lemons all the time, right? But compared to like something else, right? So, okay. Now, let's go here and then we'll talk about some of those blanks. So, with a strong acid, it is a definition classification. That a strong acid or a strong base, the word strong is used the same on both sides, means that that substance does a 100% ionization, or it fully dissociates, or in terms of an acid, it fully donates every single hydrogen. So in terms of an equation, so here's our acid. What do acids do with their proton?
They get rid of it.
Good, so draw your arrow, donate. On the other side would be,
NO3
good, so our conjugate base and
was H3O.
what I want you to circle about what makes this a strong acid is this arrow. Strong acids, by definition, break apart, dissociate completely. So all of this becomes this in solution. You actually don't have any of this floating around because all of it goes the whole way. What we'll see in a moment is with weak substances is they exist in equilibrium.
So on our notes, we have arrows just like that. Does that mean there's salts?
Oh, like on the first one?
Because yeah, on like the 8th one, they just
I don't even know. Did it have both or did it only have full arrows?
only
I might have done that just because we hadn't learned yet and I didn't want to confuse you. But generally speaking, moving forward, that is a way you can tell if something is strong or weak is by what type of arrow is in the problem. So I'll have to go back and maybe fix that. Joel, did you have a question?
So with this, does that mean that there isn't really like an equilibrium to it?
Yeah.
Does that mean there's a point at which you can put it all so there's no water in the solution afterwards? Since you've put in so much
Oh,
reactant.
I guess theoretically, yeah. Yeah, theoretically, if these were in a 1-to-1 ratio, right, you wouldn't have any water left.
Would that technically still be aqueous?
Yes, because it's still in. But there's no. I don't know, Joel. That's a good question. I also don't know what polarity that would mean. Yeah, that's a great question. So with this idea, there are 7 strong acids, and that's it. Any other acid is a weak, by definition. They're listed right here. I need you to put a big star next to this list and say we need to memorize these. Because it tells you a lot by knowing what type of substances it is. There may or may not be like an extra credit quiz next time of like listing the strong acids. So
Are you saying that there will be, or are you saying that
is the extra credit go in the test section?
So,
She doesn't want to be strong.
is there like a pattern with how it shows all
Yeah, wait, what are we, the ones that are next to
Kinda.
monochromatic acids?
So these are our acids, right? So we have, so monoprotic means there's just one H attached to it. So HCl, HBr, and HI are in the same family, so there's kind of a pattern there. But you skip F, so HCl, HBr, HI are all
What
strong.
about HF?
And then the other ones, don't know, there's not really much. So there's nitric acid, which is HNO3, HClO3, and then HCl4, which is chloric acid and perchloric acid. And then diprotic just means this one has 2 hydrogens on it, and it's sulfuric acid. So what we want to know is that if I see one of these formulas in a question, your brain says, all right, this is strong, it's going to break up completely. And you'll see why in a moment why that matters so much. Now, let's come to this second equation. This equation and this equation are the same thing. This is the most exactly, I guess you could say, or the like accurate depiction of what goes on. This is the simplified way in which you can write it. So instead of including water, you can exclude it and just show the substance breaking up, kind of like with our solubility. So this breaks up into H plus and NO3 minus.
Oh, because the water's already there.
Yeah, because the water's there, and the thing to remember from last time is that this and this are the same thing. This is just like the lazy way of doing it, but this equation and this equation represent the same process. Okay? Yeah?
It's interesting, like the thought process of chemists and stuff, because some of them are like sometimes it's like they get like into like all the nitty gritty details, and then sometimes it's just like, let's just turn this into an H plus because it's easier to write.
You really are though, like, if you go on and take organic chemistry and like, I guess I shouldn't say lazy, I really feel like it's like more efficiency maybe sometimes, but it is funny, I agree with how like, in this one case it's so detailed and then other times it's like, oh, this is fine. Okay, so let's look at this problem here and see why it matters if something is strong versus weak. Okay, so the question says, what is the pH? So circle the goal. What is the pH of a 0.04 molar solution of HClO4? Okay, so our goal is mathematically, not in a lab setting, but mathematically we want to calculate this substance's pH. Now, here's how I problem solve. It wants me to find pH. So then my brain says, well, what is pH? Good, so I write that down. So pH is the negative log of H plus. Right? Ask questions to the question to get you to the answer. Okay, so if pH is negative log of H plus, what do I need to find pH? I need to find out how much H plus is floating around in my beaker. So I think you guys already have your equation there, right? Write mine in here. Okay. All right, everybody, are you ready? It is rice.
Oh my gosh, I feel like I haven't even missed the class period now.
This is where I was gonna throw rice in the air. No, I know. I actually had rice for lunch, but it's already cooked, so that would be kind of.
Yeah, Alex threw someone to lunch rice. It was an accident.
But it was, you were just knowing.
I'm not talking about
Wait, that's it reacts immediately, isn't it just plus
It wouldn't
0? Like,
So much in it, and then it just, you find it in like 2 years.
Forever, it always
You know what would be amazing?
Okay, now, the idea of why we need a rice chart, and hopefully what you'll see, there's a purpose in which I'm doing a rice chart because it's really not needed. But me showing it to you will hopefully recognize why it's not needed. The idea of when you use a rice chart is when you need to know how much of a substance is there after a process has happened. Right? So E stands for end or equilibrium. Okay? What do I know about this solution initially? That's what I stands for.
It's a strong.
I know it's strong. Good. What else do I know?
there's 0.0.
There you go, guys. So I know the initial molarity. Now, do make a side note in your brain that molarity can only be used in a rice chart if volume isn't changing. Otherwise, it gets weird because volume changes molarity. Okay, so we know this initially, which means these would initially be 0. Okay. Now, Harry, what did you say we also know?
It's a strong acid.
Hey, what does that tell us?
That it's gonna dissolve, like it's gonna go.
Oh, it's gonna be 0 at the end.
There you go, good trip. So this is all going to go away, which means how much of it is reacting?
100% of it, so minus 0.4.
Right, all of it, because it's a strong acid. So this goes away completely. Now the change is always based on the ratio. So if this decreased by that amount, this would increase.
By the same amount.
Good. Don't split it in half.
Oh.
1 plus 1 mole doesn't always equal 2 moles. In this case, I don't know how you would say
One
that.
mole minus one mole. So that 1 mole changes to 2 moles.
Yeah, just because they're splitting up, right? Okay, so now we know the amount of this. We don't really need this, but that's what it is. And then I can take this, plug it into there,
And you get 1 to 2.
and if you're estimating it's 1 to 2, in my calculator I got 1.4.
Yeah.
I'm not wrong.
Okay, now,
Wait.
notice, draw another arrow for me here, that what we plugged in here ended up being the same thing that was given in the problem.
Is it always that?
When would it always be that way, Grant? If it's strong. If it's a strong substance, you don't really need a rice chart because it always goes to completion. And for acids, it's also always 1 to 1 because it's just 1 proton leaving. So
Wait, what about the one where it's 2 protons leaving?
it loses them in steps.
Isn't citric acid, doesn't that?
So when something is diprotic or triprotic, it never loses it all at once, and each step is actually a different acid. So like sulfuric acid H2SO4 turns into HSO4 minus, and that's not a strong acid actually. So, does that make sense? Yeah, good question though. Sam?
So, on the test, we'll ask for like the exact pH or like an estimate.
If it's multiple choice, then it would be an estimate. If it's free response, give exact.
How did you use it again? The number of less.
You just go, you have to convert it into scientific notation to have a power of 10. So this would be 4 times 10 to the negative 2. And then it's going to be in a range of 1 less than the exponent.
Right. Okay.
Yeah, good
What's
reminder.
the sodium hydroxide?
So-
I just have a question. How come you don't split it in half on the other side?
Yeah, so think of it as, so like, if I have one of these, okay? Let's call it, oh, we'll do this. Okay. Okay, so this together represents HClO4. How many HCl4s do I have?
1. Wait.
1. If it breaks up, how many H's do I have?
Shouldn't the,
And how many Cl4s do I have? So because it's a substance breaking up, the amount hasn't cut in half because you still have 1 H and 1 Cl4, but they're now not together.
It's also polarity.
Yes. Yeah, it's not grams. Like if this was a mass thing, mass would cut in half. If it was any other unit besides the mole, it wouldn't do this. But because mole is literally a counting number, like we're literally counting things, it doesn't get cut in half. Does that answer your question?
it's a chloroform.
It's a what?
It's ClO4, it's chloroform.
Oh,
It's like, it
can you
sounds
read
like.
it?
Yeah.
It's like, what do you even say? Okay,
That's funny.
any other questions on this?
How do you know, like, how do they find this strong acid?
In history, I'm not entirely sure. I mean, it's just, I'm assuming because you eventually you're going to a place where we can measure the amount of like H plus and stuff, right? And so then they just were to determine that the amount of H plus that was came out is like the same amount as the oxygen that went in. But I'm not entirely sure in history. I don't know when they were officially like. Good question. Any other questions on this so far?
So, like, for all the ones that are listed, it'll be the same amount, like, if you put points before it.
Yes, and that's why you want to have to memorize, because if a problem comes up and says, hey, find the pH of this substance, if it's a strong substance, it's a really easy problem. But if you're going to see when they're weak, we have to kind of do some different things. So,
Can you say again why that when it's strong?
because by definition, strong acids dissociate or break apart 100%. So if I put 50 of them in, they all break up. So it's always minusing. You never, I guess with strong acids, you always have 0 of the initial reactant. Always.
So even if you were to, the water was to be the limiting reactant, or were we just not coming across
Yeah, good thought though, because that would technically influence it, but water's always in excess. So, okay, strong base is a very similar concept, except for now it's a base, but same thing in that it breaks apart or reacts completely, 100%. We do need to memorize the strong bases as well. These ones do have a nice periodic table trend though, so it's a little bit, I don't know, a little less memorizing because it's kind of on the periodic table. So they're listed right there, but what it means by alkali metals, that's group 1, so column 1. Now hydrogen's not a metal, so it doesn't count. But below hydrogen, so lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, these don't really exist, but if they were, they'd be strong. And then starting at calcium,
What do you mean they don't
Does it get
exist?
stronger the further down?
it's like this one's so radioactive it never bonds with things.
Well, 'cause it-
Oh, that's
Here,
why
like,
you say it exists, but it doesn't, it can't become other.
Like, yeah, like, no one's ever
it
seen
basically,
it.
Surely
breaks
exists
apart.
because-
And it's like, but what's left is actually the
Or
base.
it was-
Does the further down on the thing that we go, does it get stronger or does it get weaker in the base? Or is there like not actually a trend?
That's a good question. From what I know, Milo, and the kind of same thing with the strong acids, we have the 7 strong, but there's not a classification within that. Like, it's not like this is the strongest of the strong. It's like, these are just all strong, and I'm pretty sure it's the same with the bases. Because if you're 100% ionizing, and they're all doing that, right, like, how can one be stronger than the other? So, yeah, great question, though. So, let's look at this problem here. So, just a reminder, in case you're confused by my word, OH is hydroxide.
Does that just have, like, there's not really a super, dissolved, like a super soluble, since they're all, like, no matter what, it'll still be like the same amount of, like, solubility, well, being able to react?
Ask that again.
Are they all just as reactive? Like,
Yes.
reactive?
Yes. So, of the 7, well, of all the strong, there isn't a classification within the strong.
So no matter what way that, like, you, like, use them, they're still gonna be the same level of acidic basis?
Yep.
So no matter if it was like sodium hydroxide and hydrochloric acid or cesium hydroxide and hydrochloric acid.
Same thing. Yep. Yep. In terms of their strength. Okay, so we have sodium hydroxide here, NaOH. Okay. As a strong base, once again, emphasize the full arrow here. It doesn't go backwards. It separates into Na plus and OH minus. Once again, the amount of OH is what classifies something as a base. Now the question is the same, that it wants pH. I'm not going to set up a rice chart this time because we realize it's not needed, but we do need to recognize that, because how do I find pH? Negative log of H. Do I know how much H I have directly?
No, we only know how much OH we
Yeah, so I know how much of this I have.
So we use the other one.
There we go. So there's a few options for equations. My preferred way is doing the POH. This is what Brandon was talking about in the beginning, I think. So POH is just the negative log of OH, right? So then I'm just going to plug in the negative log of 0.028. And I got 1.55. Yep.
Yeah.
Now, right off the bat, you should recognize that can't be the pH. Because bases, right, that doesn't make any sense. So the reverse, or to get it to the pH scale, is 14 minus. So 14 minus POH equals pH. So 14 minus 1.55.
Nice, so it's 12 and 1.
Which does make sense. Questions on that one? So when something is strong, the concentration given is telling you the amount of ions that are made. And so you literally can just take the negative log of it, and then sometimes you might have to flip it if it's a base to the pH scale. Yeah.
So then why can't 1.5 be the base?
So on the pH scale, less than 7 is always acid. But the pOH scale is reversed. Any other questions to clarify that? Okay, for a smiley face. Don't say anything out loud.
You're gonna react to things.
Yeah, like I said, in this unit, a lot of things look like water.
That's why I asked for
Feel thirsty. Okay, don't say anything out loud. Okay? So in this flask right here, in this beaker, I have hydrochloric acid, HCl. Okay? In this beaker right here, I have acetic acid. So by definition, this one is strong, this one is weak. Okay? I'm going to add what is known as an indicator to both of them. Indicators indicate pHs based on color. This one in particular is called the universal indicator because it does all the pHs based on the rainbow. So 0 is, or 1 is red, and 14 is purple. Green is neutral.
I remember that.
Yeah, I can't answer that question. But it is pretty amazing.
What is red again?
It's so
So acids.
So right
So
now,
acids are red, bases are violet. Yes, yes. Okay, so what I want you to predict before I do it, okay, so this is check my labels, hydrochloric acid, acetic acid, strong acid, weak acid. Okay, make a prediction in your head of what you should see pH-wise. Don't say it aloud. Are they going to be the same? Is one going to be lower? One going to be higher?
Ooh.
wait, were we supposed to talk about that?
No, don't say anything yet. Just say it in your own head. Talk to yourself.
We're not pointing in the direction.
Not yet, because I've given everyone a chance to think. Okay, turn to your table buddy and whisper to them what you think. You're missing your bag.
I haven't had one.
It's true, I forget, because a lot of times it's right over me, kind of throw stuff. Okay, finish up your conversation in 5, 4, 3, 2, 1. Okay, now, let's see.
Sticking to it.
Okay, here we go.
This is gonna be so fancy.
Yeah.
Aha!
Okay,
So that looks like fruit punch. Really good. Don't drink it.
ready?
I don't think you want to know this one.
What?
Okay, now, as long as you had a discussion with your neighbor about a prediction, you can have a smiley face for trying, because I appreciate effort. But now I want you to answer the question of what Joel just asked me. So you got 1 minute, turn to your table buddy and see if you can come up with an explanation of why are they both the same. Okay? So this one's strong, this one's weak. Why are their pHs the same? Okay? Do you have an answer to the question?
I wonder, I have
Okay, first off, I love the question that I heard a lot of you ask about the question. You're developing those problem-solving skills of like, well, I don't know, but let's start thinking. And I heard a lot of have you say, well, okay, well, what is pH? Like, because that's what this is showing, is this is showing that their pH is the same. Okay, Joel, what's your theory?
So, since pH is like the amount of hydrogen.
Okay, pause, I'm gonna repeat that. So pH is the amount of H plus floating around. Continue.
So because of that, it might have been that the weak acid had a higher molarity, and because of that, the equilibrium of it was a lot higher, and so there was more H plus in that. And then the other one reacted completely, so all the H plus is there, but it's not as much.
Well done, well done. So pH, so what I wanted to make sure we separate here is being strong just means it's going to break apart completely, but the factor you also have to take into account is the concentration that's being put in. This right here is a 0.01 molar solution of hydrochloric acid. This is a 2 molar solution of acetic acid. So even though it's weak, I used a much higher concentration so that in the end, the amount of H plus is actually the same in both. Does everyone understand the difference of pH and strength now a little bit?
But, so if the H plus was the same in both, like the whole, like, it would have turned kind of yellow.
Very good, yeah. No, very good, Shane. Yeah, if they're the same, then the strong one's always going to be lower because it goes all the way. So that's what I should have done. I should have made a 0.01 to compare. But yeah.
Was the goal to get them the same color? Or was it to get the higher concentrated?
Whose goal? My goal?
Your goal.
My goal is to confuse you. No, I wanted them to be the same. Yeah.
Okay.
I wanted you, because a common misconception I've seen throughout the years is that misconception of, oh, this is stronger, so it must have a lower pH. But that's not guaranteed to be true because you have to look at the concentration as well. Aiden.
We can actually smiley face and tell it right if the prediction is correct.
Yes, if you said something along what Joel said, you can have a second smiley face as well. So, Sam. If they're the same concentration, because the strong one always goes 100%, but weak ones we'll talk about in a second, typically go like 5%, and that's it. So if you start with, imagine starting with 100 of each.
Welcome back.
The strong one's gonna go all the way, so 100 to 100, but the weak one's only gonna make about 5.
So does that mean that you use like that would mean that it would react? Well, I don't know how it
Does that answer your question?
It's not like 40 left.
Was it possible to get 0% of the test when you travel it?
The more H plus there is.
Not right now.
Actually, that's right. You're now like a C, so.
Because it was a 0.01 molarity. So I used 1,000 less.
Yeah, I did tell you like the student council. When the term happens, because that's what it'll be.
Yeah, so if you start with the same molarity, then yes, the strong one's gonna definitely have a lower pH. But I tricked you because they're not the same. Yes,
Okay, so my prediction was that they're both acids, so it will be red until it reacts like is that wrong?
yeah, because acids can be anywhere from 1 to 6. So red, orange, or yellow, all acids.
But then what's the reaction? All of its phases, it'll
So then it would change it, yes. Yeah, you are right that if you were reactive ones are going to change, but acids don't technically have to be red. Yellow. Yeah, so it means red, orange, or yellow.
If you were to mix together, if you were to mix together an acid and a base, they neutralize each other? Does that mean like the H pluses and the OH minuses that are floating around just like make water?
Hold that question for, we'll kind of address it a little at the end today, but we'll really address it next week. So hold that for now. Because you'll understand the answer better. But yeah, great question. Okay, let's get to weaks now, everybody. Okay, so we know that strongs dissociate 100%, right? If I put 5 strong acids in terms of like individual ones, all 5 of them are going to break up. Weak ones do not. So circle that arrow right there. This is key. Weak acids do not dissociate completely. They are in an equilibrium state, meaning some of it breaks apart. So some of it does become H plus and the conjugate. Once again, a reminder for those that weren't here last time, HA is just a generic way of saying an acid without having to be specific. We honestly use them a lot with weak ones because there's so many weak acids, but it could represent a strong one too.
Oh, so if it's a strong one, then you know that it.
Yes, very good, Allison. Yep, you would know by the arrow. So with this idea of it being weak, I'm going to flip to a picture. You have it on yours, but just so you can see it. If we could zoom in molecularly to a strong acid, you would only see hydronium and A minus. That's it. In a weak substance, we actually have a lot of HA. So if you, I know it's kind of small on your paper. I should have made that picture bigger. But you have a lot of HA still floating around because some of it doesn't break apart, right? It stays linked together. Now, because it's an equilibrium system, this is going to now connect to our equilibrium unit in that it has an equilibrium constant. Just like all our equilibrium constant, it's represented by capital K. We put a little a next to it just to say, hey, it's an acid equilibrium, but it's still the same setup. So what is the setup for an equilibrium? Products over reactants. So if that's my equation, Ka would equal H plus A minus, those are your products, over reactants.
And will most weak reactants have really low molarities? Not low Ks?
Molar is whatever you want it to be. But the Ks are always very small, yes. Now with this FYI, this is on your formula sheet actually. This generic setup for Ka. I don't really know if it's necessary because it's like all equilibriums, but it is there if it helps you out. So going off kind of what Joel said, let's talk about this magnitude of K. So we talked about K's all last unit. So turn to your neighbor really quick and remind them if K is really, really small, what does that tell you about the solution? Tell your neighbor, make sure they know. If K is really, really small, what does that tell us?
So would we be figuring out if like this string there it is.
Okay, if you said something along the lines of a small K means reactant favored, or there's more reactant in the products, you can have a smiley face here. And then take your pencil and star and underline and circle all things this sentence. Okay, emphasize this sentence for me. I know I already bolded it, but emphasize it again. So when K values are something that will most often be given to you because they're just known constants for an acid. Every acid has its own unique one, but the Ka is something that can be given to you, and you need to recognize what that is telling you, right? That K value helps you understand how weak of a weak acid it is, or is it maybe more on the stronger side of the weak acids? So kind of let's go through. So we have acids. Acids can be weak or strong. Within the weak has a classification as well, where something can be classified as a weak, strong acid, or a weak acid.
Strong weak.
Did I say that backwards?
Yeah.
Rewind. It could be a strong weak acid or a weak acid.
Or can there be a weak, strong acid?
No. So on the strong side, there is no classification. It's just they're strong and they're all strong.
Because there's no like.
Because you
it's
can't
not
go
like
over
they're
100%,
changing.
right?
Yeah, they're not changing. It's just 100%.
Thank you for clarifying that. Might be confusing. Yeah.
How can hydrofluoric acid be a weak acid? That's just like it's so reactive.
So that's where, so that's another great point to point out, is strong and weak, once again, are just telling you their behavior in terms of dissociation. But we can have very, very dangerous weak acids. Like, don't be deceived, right? Or very, very reactive weak acids.
What's the most
Oh, I
dangerous?
thought there was a difference. I thought they were like strong. I thought strong acids meant that they were like super reactive.
No, weak acids can be just as reactive. The difference is they just don't dissociate 100%.
What's the strongest weak acid?
Probably hydrofluoric.
Is that the strongest, like, well, not strongest acid, but like the most reactive acid?
Do we have to memorize that? What is the most?
Because I feel like mixing like cesium hydroxide and hydrofluoric acid would be one, entertaining, and second of all.
Okay, circle this number right here, and we're gonna label it. So circle this Ka up at the top, everybody. Circle this Ka, 6.8 times 10 to the negative 4. Now recognize, these are all weak acids, because they all have equilibriums. But label this top one as a strong weak acid. And then I want you to label the bottom one as a weak acid.
So like the bottom one, could you just like touch it? Do you say that?
Well, once again, you've got to be careful about, because concentration plays a big role too. But yes, generally speaking, if something is a weak acid, then it's barely making any H+, which is what is dangerous to us when we touch it.
It's not very.
Why is H+ so dangerous?
Because it just reacts with most.
Oh, yeah. Like it likes to just like
It'll eat us
steal
up.
electrons from the
Oh!
Yeah, so
that
most
makes
things it just
sense.
reacts with whatever that thing
So
they need.
technically, H+ is actually the most dangerous acid.
Yeah, by itself for sure.
It's like
Harry than awesome.
So that means that our body is more basic, meaning that we would lose our own hydrogen.
It's actually like
Is that possible? Like,
Well, I guess because remember how like things can behave like a base but not be a base?
yeah.
Like how
So,
water. So
yeah.
I'd say like that's kind of like I wouldn't say our body is a base.
But like it's kind of like.
But if an acid goes on it, it's going to act like one that's just going to start.
Yeah, and that's why it hurts because it's the reaction. Okay.
Is that why bases are so reactive with other stuff? Because it only accepts protons. It doesn't.
Are you on the line?
Like the reason that acids are super reactive is because like they give off electrons or stuff, and bases are only reacting on stuff with protons, right?
Yeah. Yep. So then you don't see the reactive side as not being less reactive. So. Okay, last thing, and then I got another mind demo to make you think. So another way, so Ka's tell us, right, how much something is breaking apart. The bigger K is, the more it's breaking apart. The smaller K is, the less it's breaking apart. We can also measure and report what's known as a percent ionization, which is literally just the percentage of how much has broken down. So the equation for percent ionization is H+ over HA. And then times by 100 to make it a percent. So this is telling you of the original, how much actually broke up. Once again, meaning if I put in 100, how many actually became H+. And generally, it's like 5% for weak acids. Like 5% or less. Like they are very, not very much of it is actually ionizing out. So, yeah.
So how do you, like, when do you know it's like a strong weak acid? Like what number?
By are you talking about a strong weak and a weak weak?
Yeah. Like how do you, like, what small, how small can you get before it's
They really more comparison terms than anything else. There's not a hard line. So it would never be like, I would never just give you a weak acid. I mean, sometimes you can if it's like a drastic one, like 10 to the negative 10. But there isn't a hard line of like, oh, everything less than this is a weak weak. But it's more of if you are given a list of themes, you should be able to recognize within that list, like, oh, this one is the strongest of these weak acids, and this is the weakest. Does that make sense? Yeah, great question. Eden?
So why is there like that gap in acid, right? Because it's like 5% ionized, but then with like strong acids, it's like 100%.
Yeah, I don't know. Someone asked me that last grade too, and I don't know. It's a great question of like, why is there no in-between ground?
No, there's
Isn't there
something
medium?
Like medium acids? I don't know, yeah. I'm not sure why. I'll have to research it more. But yeah, still great question. Just any acid, so the original acid. reactants. So it's kind of like the original, like here's your equation, right? So it's like the original. Okay, everybody stand up. Stand up for me. Stand up, stand up.
Alright, someone check those.
Okay, who's thirsty? Russian roulette.
Wait, actually?
I'm just giving you a second to stretch your legs.
I want to see you like mix together a dark purple one and a bright red one and then just turn green. And it's gonna be.
She's probably gonna do that.
Did I just predict it? Did I predict it?
Okay, everyone got a good stretch in? Okay, sit back down. Okay, I'm gonna tell you not very much about this
We're just gonna figure it out first.
because I want you to just come up with an answer.
Is it like,
Okay? So here's all I'm gonna tell you, and then you're gonna watch, and then don't say anything out loud because I want everyone to think for themselves, and I'll give you a chance to share. But I want you to just come up with an explanation based off what we've learned with acids and bases so far. Come up with an explanation of what you're about to see. Okay?
The indicators.
Go ahead, wait.
That's pretty much all I'm telling you.
Oh, come up with it after. I was like, wait.
You're like, what am I seeing? I point to do something. Everybody ready?
No. You're good now.
What was that already completed?
what?
What the heck? Why did it move like? Why did it do that?
What?
Strawberry.
Yeah,
It starts out.
Someone's, is that
They look like they have
It's gonna be blue. Blue.
That's
Base. Ooh.
And then purple.
Purple.
Whoa,
Purple. Oh my goodness, that is a really good purple.
that's really satisfying.
I lost yellow. We are missing one of the rainbow, but.
Wait, you should mix them all together.
Yeah, yellow is really hard to get, right?
Okay, I'm gonna do some more things to it, but turn to your table, buddy. I'll give you a minute. Explain it. How'd that happen? Ready, go.
Whatever she wanted, the teacher's just trying to trying to trick us again.
Yes. No, I'm trying to like nothing.
That's what I thought.
Just like what can you, based on what you know about acid bases, come up with an explanation. How would I do that? And it's all magic. All right, 5, 4, 3, 2, 1. Okay, as long as you didn't say I don't know and not try, you can have smiley face.
You said I don't know.
You did say, I don't know, and then we tried.
Yeah, as long as you try. I know sometimes you like to preface that just to like.
What if you don't say I don't know, but you?
Yeah, so if you didn't, if all you said is I don't know.
You get a friend.
No frowning face, but try next time. Okay, we're gonna come back to this. I'm not gonna give it away quite yet. Okay, let's look at this problem.
I'm excited to see them like.
I will. Just stay tuned. Just making sure no one like turns off or